We continue with the study of the spectrum. This time we will talk about operators on a Hilbert space. Okay, so I want to recall once more the theorem which we proved long ago. So we have that if VW Banach and A belongs to LVW, then we have range of A closed if and only if range of A star is closed. And then we had the following result, namely A is on 2 and then norm of A star phi is greater or equal to C times norm phi for every phi in W star, and then range of A star closed and null space of A star equal to 0. So these are all equivalent to each other, and this is the theorem which we had. So now we prove a lemma, very useful lemma which we will use again and again. So H Hilbert space and T belongs to L of H. So it's a bounded linear operator from H into itself. Let assume T has closed range and that T and T star are both injective. Then T and T star are invertible. So proof. So T has closed range implies T star has closed range, and so plus T star is 1 is given to you, and therefore these two imply that T is on 2 by the theorem which we have just stated. So T is 1 on 2 continuous, and therefore by the open mapping theorem it is invertible, and that also again implies that T invertible means T star is invertible, as we have already seen yesterday. Okay, so T and T star are both invertible. So this is a very useful lemma which we will have occasion to use today again and again. Okay, proposition. So H Hilbert space over C, okay, and this is important, such that Txx equal to 0 for all x in H, then T is equal to 0. So okay, so we have, so proof 0 equals T of x plus y because for all vectors this is 0. So that means Txx is 0, Tyy that's also 0. So you have Tx y plus Ty of x, that's equal to 0. Okay, now 0 is also equal to T of x plus Iy, okay. So again Txx is 0, I square is minus 1, therefore I will come out, then you get Tyy that's equal to 0. So you get Tx Iy plus Ti times Ty x equal to 0. Now this is equal to minus I, because I should come out as a conjugate. So you have minus I txy plus I tyx equal to 0. So from these two you get that txy plus tyx equal to 0 and txy minus tyx equal to 0, and therefore this implies that txy equal to 0 for all x and y, and this implies that tx equal to 0 for all x, that is t is 0. So the complex is important in this particular result. So if you had a real Hilbert space, for instance if you take R2, so with norm 2, that is L22, then you take T given by rotation of axis by pi by 2. So that is the matrix. The matrix of T is 0, 1, minus 1, 0. And then if you take xy, you get y comma minus x, and therefore T of capital X, x. So x equals xy. So txx is 0 for all x, okay, and then t is not 0 at all. Okay, so this is it's the presence of the I which makes a difference there, and therefore that's important. Okay, so then again lemma, if you like. Okay, let H be a Hilbert space over C. So henceforth we will work over C, okay, and Tx equal to, greater than or equal to 0 for all x in H. Then T is self-adjoint, T equals T star. Again, obviously this doesn't apply to the real case, because the previous example gave you Txx equal to 0, which is a particular case of Txx greater than or equal to 0, and this matrix is not a self-adjoint matrix, and therefore you have that this is not applicable in the real case. So it depends on the complex case. So we have proof 0 is less than or equal to Txx, which is equal to, because it's a real number, this is Txx conjugate, so implies real, and that's equal to xtx equals T star x x. So we get that Txx equal to T star xx, that is T minus T star xx equal to 0 for all x. So this means by the previous proposition you have that T equals T star. Okay, so that is the proof. So now we come to a very nice theorem. Okay, let H be a Hilbert space over C. Let T belong to L of H. Then 1, if T equals T star, then spectrum of T is contained in R. So the spectrum consists only of real numbers. Okay, if T star equals T star T equals identity, so T is unitary, implies spectrum of T is contained in set of all lambda in C such that mod lambda equal to 1. That means spectrum is contained in the unit circle of the complex plane. Then 3, if Txx is greater or equal to 0 for all x in H, then in particular T equals T star, so the spectrum is in the real line, then spectrum of T is contained in 0 infinity. Okay, so if you have, this is what we call a positive definite or positive operator. So real self-adjoint operators have spectrum in the real line, unitary operators have spectrum on the unit circle, and positive operators have spectrum in the positive real line. So this is analogous to the real numbers. This, the normal operators, you can say, if you think of them as complex numbers, then star is like conjugation. Okay, so if T equals T star, that means that means it resembles real numbers, and that is reflected by the fact that sigma T is contained in the real numbers. Now T star is like saying Z bar. Okay, so if this is identity, so this looks like the unit circle, so that's exactly the spectrum is in the unit circle. Mod lambda equal to 1 means lambda bar equal to 1. And similarly, if T is a positive operator, so it looks like positive real numbers, then in fact the spectrum is indeed in the positive real numbers. Okay, so proof. So we'll prove the first one. Okay, so let T equals T star, let lambda belong to C such that imaginary lambda is not equal to 0. Okay. Now Txx equals x T star x, which is equal to x Tx, which is equal to Txx conjugate. Okay. So this implies that Txx is real for all x in H. So now you look at T minus lambda I x x. So that's equal to Txx minus lambda times xx. So the imaginary part of T minus lambda I x x, this is real, so this is nothing but the imaginary part of lambda times norm x square. Therefore, mod imaginary part of lambda times norm x square is less than or equal to, it's equal to the modulus of this, so that is less than to mod of T minus lambda I x x, that is less than or equal to norm of T minus lambda I x times norm x. Therefore, norm of T minus lambda I x is greater than or equal to mod imaginary part of lambda times norm x. Okay. Similarly, we have norm of T minus lambda bar I x is also greater or equal to mod of imaginary part of lambda times norm x. So when you have a operator which is bounded below, we have seen that it has closed range, because if you take any sequence in the image which converges, then this will be Cauchy, which will imply that xn is also Cauchy. So xn will converge, and so the image limit will be in the image. Okay, so any operator which is bounded below has always closed range. So we have, so this implies that t minus lambda I, t minus lambda bar I have closed range, and are both 1 1. Because of this condition, it's trivially 1 1. So then we have that t minus lambda I, t minus lambda bar I are both invertible by the lemma which I just proved, and therefore lambda belongs to rho of t. Okay, so if the imaginary part of lambda is not 0, then lambda is in the rho of t, and therefore this implies that sigma t is contained in set of all lambda in C such that imaginary part of lambda equal to 0, that is sigma t is contained in R. Okay, so that proves the first relationship. So now look at 2. So we have t star equals t star t equal to I. Okay, so you have, if you take norm x square equals t star t x, because t star t is the identity, that's equal to norm tx square. So these are all isometries. Any unitary operator gives you an isometry, namely norm tx equal to norm x. So norm tx equals norm x, and this also equal to norm of t star x. The same, for the same reason, instead of t star you took t star t, you would have got the same thing. Okay, so you have this. Now let us take lambda in C, mod lambda not equal to 1. So then you take norm tx minus lambda x, that is greater or equal to mod of norm tx minus mod lambda times norm of x. But norm tx is same as norm x, so that's equal to mod of 1 minus mod lambda times norm of x. Okay, and similarly norm tx minus lambda bar x, which is the adjoint of this. So t minus lambda bar is nothing but, so let me make that remark here also. Okay, t minus lambda bar I is nothing but t minus lambda I adjoint, because t star equal to t, and when you take the conjugate of lambda you should get lambda bar. Okay, we have seen those properties. So this is also greater or equal to 1 minus mod lambda modulus times norm x. So once again, t minus lambda I, t minus lambda bar I, which is nothing but t star minus lambda bar I, which is t minus lambda I conjugate. Okay, have closed range and are 1 1, so implies invertible, implies lambda belongs to rho of t, and therefore you have that sigma of t is contained in set of all lambda in C such that mod lambda equal to 1. Okay, so now we come to the third one. So you are given that txx is greater or equal to 0 for all x in H, and of course we have seen that this implies t equals t star. Okay, and therefore sigma t is of course contained in R. Okay, now t plus, so let us take lambda positive. Okay, so then t plus lambda I x, lambda is a real number, positive real number, t plus lambda I xx is greater or equal to, so that is lambda times norm x square. Okay, and therefore norm of this by the Cauchy-Schwarz inequality, norm, so lambda times norm x square is less or equal to norm of t plus lambda I x times norm x, and therefore norm of t plus lambda I x is greater than or equal to lambda times norm x. Okay, so once again, and then its conjugate t plus lambda I star is the same as t plus lambda I again, because lambda is real and t is self adjoint, therefore this is the same, and therefore this implies that t has closed range. So t plus lambda I has closed range and is 1 to 1. So this implies t plus lambda I is invertible. So this t plus lambda I is nothing but t minus lambda I. Okay, and therefore for every lambda positive, minus lambda belongs to rho of t, that is lambda negative implies lambda belongs to rho of t, and therefore this tells you that sigma t is contained in 0, infinity. So with this we will wind up this chapter and then do some exercises next.